Hello, everyone, and welcome to the webinar. This webinar, again, will be on simultaneous 5-axis, and this will be the fifth part on this webinar, given by Ahmad Onkar, our specialist in 5-axis simultaneous machining. Before we start the webinar, I'd just like to mention to everyone and remind everyone that we have our conference coming up. It's SolidCAM World in May, between May 28th and May 30th. You can all sign up on our website. We're getting closer to that date now, so please sign up as soon as you can. And we have a complete venue for the conference itself. Extremely interesting, and there's definitely something there for everybody. Okay, without any more further ado, I'd like to turn this over now to Ahmad and make Ahmad the presenter. And Ahmad, you can unmute yourself and show your screen.
Thank you very much, Sydney. Hello, everyone, and welcome again to our session 5 of 5-axis webinar. It's going to be a series. We're going to have a few more. I was asked after the last webinar to show a couple of options that probably I missed showing in my sessions last time. So I'm going to touch upon those two seemingly important options for people who are clueless about the options. Okay, so we are going to see about an option called 3D tool compensation. Now, this particular option basically comes from SolidCAM, and it's introduced into the 5-axis engine. So what this basically does, so you have two options in 3D tool compensation. One is a tooltip and tool center. So if you look at the definition, this looks very similar to the definition of our regular compensation, but the difference here is that you could get the output in two different ways. One is to represent it as a tooltip, and the other one is to represent it as a tool center. Now, for people who have been trying it, okay, I also tried it honestly last week, and I did not find any difference in the toolpath. Okay, so for people who have been attempting it and seeing that there's absolutely no difference in the toolpath, we need to hang on ourselves right now, because it doesn't make any difference to your graphical toolpath. What is, however, different is the G-code itself. Okay, so thank you very much, Daniel, for sending me this picture, which I've put it in our presentation. So every tool, when it does a 5-axis computation, has got basically 6 positions. The surface coordinates, represented by X, Y, and Z, and the tool axis vector, which is represented by either angles that are calculated or the vectors itself. For example, in Heidenhain, it could be represented by Tx, Ty, and Tz, that is tool vector along X, tool vector along Y, and tool vector along Z. Wherein with Siemens, it's represented as A3, B3, C3. For many of you who are using Siemens Post, when you're running a 5-axis code, you will see that these are the output that is coming, one of the output. And Herco gives out the IJK. Also, in the latest FANUC controls, you have got G43.5, which will output the vector, okay, tool vector. However, when you switch on the 3D tool compensation, especially in posts that are supporting this feature, you will see that there are additional 3 vectors coming up in your program, and that is NX, NY, and NZ. These are basically the surface vectors or surface normal vector of that particular point. Or if it's Siemens, you will see A5, B5, and C5. If it's Herco, you will see UVW. I'm not very sure about FANUC, what it does with G43.5. Okay, let's look at a simple scenario where your 3D tool compensation is switched off. A Heidenhain output will look like that. You have L, X, Y, and probably Z, and then you have C axis and the A axis. Okay, that's how it's probably represented. You have those 5 coordinates. If it is Siemens, then you will see that X, Y, again Z, and C, and the A angle coming out. This is a scenario where your 3D tool compensation is not switched on. The moment you switch it on, you will see that if it's a Siemens output, you will get this function called as cut3cc, or which is basically switching on the 3D compensation. And in your toolpath, you will see X, Y, Z, A3, B3, C3, the tool vectors, and then you have A5, B5, and C5, the surface normals. Okay, so you get all the 6. Now, what is the advantage here? The advantage are quite a lot. For example, if there is a tool wear, okay, and the operator wants to replace the tool, he can do that even without changing the program. Or, for that matter, if the tool breaks, the operator can change to a different tool with a different diameter and even a different corner radius without having to change the program itself. The controller knows that there are these 6 values, and it also knows the tool that is being called, especially if it's Heidenine, because in Heidenine we don't output anything. We just output the 6 vectors, tool and surface vectors, and it knows the tool, so it readjusts this position based on the new tool and the old program. Okay, so the gist of the whole thing is that if it's a 3D compensation is switched on the toolpath, there's absolutely no difference on the graphical toolpath. But if you go into the part itself, then you have the G code, you have a completely different output. Okay, so where do you look for this? Okay, let's go into our GPP, because I moved a lot into GPP. Okay, let's edit with Notepad, and let's look for a line which is called as compensation 3D. So you need to look into this line whether your post is supporting this option or not. If your post is not supporting this option, then no matter what you're trying to do in those 2 tooltip or tool center or switch on or switch off, you will not see any difference in your G code. So it's important that you need, or your post should support this option. So if you have any questions, you need to get back to the post developers to understand if they can put this option in your GPP or not. Okay, so let's again just quickly look at the part itself. So I have the part out here. Let's edit this toolpath. I have got a bullnose 10, a ballnose 10R5 in this case, and if I go into my tool parameters and modify, it's currently switched on. So let's switch off, save it, and I'm going to enable the Siemens one because you can see that option there. Okay, continue. Let's calculate this option. And let's generate a G code out of this. Okay. You can see that we do not have the cut.cc command because we have not switched on the compensation on. We have not switched on the 3D compensation, and all I see is X, Y, Z, C, and A angles. Okay. So we have not switched on any of our compensation at the moment. Now let's go back and switch on the compensation. So modify, switch on, and I'll switch to the tool center compensation. By the way, you will see 2 different values also in coordinates when you move from tool center to tooltip. Okay, so let's generate the G code, and you can see that it introduces the cut3cc function. Now this has to come from the post, so it's imperative that your post must support this option, and also the fact that you see you have X, Y, Z, A3, B3, C3, A5, B5, and C5. So you see all the 6 vectors, 3 vectors from the tool, 3 vectors from the surface. Okay, I hope that this part is clear. It's more controlled by the GPP, and you can see that there is absolutely no difference in the toolpath. As far as the toolpath is concerned, there is absolutely no change in the toolpath. Okay, the representation still remains the same. Another question I was asked was about the feed control and how it works. Feed control also is a pretty useful and important function in 5-axis. By the way, the compensation 3D works only for HSS and Sim 5-axis. So you'll not find this in our HSM functionality, but because our HSS and Sim 5X support this functionality. Okay, so let's edit this, and I have my tool in that I have put my cutting feed as 100. So what I'll do now is I'll just run the simulation slowly, and you can look at the feed rate. Basically, the feed rate is constant. It's not changing. It's remaining 1,000 all over. With the feed control, I can enable or disable control of feed rate in certain areas. For example, I'll enable the feed control, and I will say the feed must be controlled on this surface, okay, the small radius, because here I want either the feed to drop or feed to run very quickly, okay. In our case, I would like the feed to drop to 50%, okay. So I've selected the face, say okay, and let's calculate. Let's run the simulation and see what happens, especially when it comes to this area here, okay? So I'm going to zoom there. It's constant at 1,000, and the tool is now coming up here. You can see that the feed is still not changed. It's a puzzle for many of us why the feed didn't change in spite of giving that surface as an area where the feed had to reduce down. The answer is quite simple. I have defined the feed. The feed control works only when the surface actually intersects the tool. So the surface actually has to pass through the tool for the tool to understand where it needs to drop the feed rate. Okay. Now, in order for the surface to intersect, I cannot keep the offset value as 0. I need to have a different offset value. At 0, the surface is not going to intersect the tool at all. It will just roll over the surface, and it will not find any zone to drop the feed rate. So I'm going to give a feed rate, or rather an offset of 5 millimeters for that surface, and I'll say inside that offsetted surface, reduce the feed by 50%. Okay, let's run the calculation. And let's run the simulation again. Okay, it's still 1,000. And as the tool now comes closer, you'll see that if this surface was offset 5 millimeters, where would it end up? And you can see from that particular point, my feed rate drops to 500, which is 50% of the cutting feed rate. And it will traverse that entire length of that offset surface with that particular feed rate. When it exits that surface, that offset surface, you will see that the feed rate will now return back to normal, which is 1,000. Okay, the moment it leaves that offset surface, it's out of the area, and it now returns back to its normal feed rate of 1,000. So the feed control will work only if the surface that's been given as a zone intersects the tool. If the surface doesn't intersect the tool, then it will not drop the feed rate. Okay, so very clear about that. So that's how the feed control works. All right, so I will move to a completely different topic now. We have seen our generic 5-axis in the last 4.5 sessions. We'll now move to the application-based specific strategies that are there in our 5-axis portfolio or 5-axis offering. And today we are going to see the multi-blade technology, how multi-blade works on impellers and parts like that, and how do we really need to work with it. So let me open a part. I already have a multi-blade part with me. Okay, it's basically a part that consists of several patches of surface. So what I've done basically is to make my job easier today in the webinar. I have just defined some colors, which makes it very easy for me to select these surfaces. Okay, so how do we work with Multiblade? First of all, working with Multiblade requires two things. One is your part, and the other one is your stock. Okay. Now your stock could be a simple round cylinder or any other shape that you deem fit to be starting with. But in most of the cases, the starting stock is basically a turned part that is given as a starting stock to the Multiblade function in SolidCAM. And what I have here is a simple turned part. Okay. I've developed the curve and I've revolved that curve to generate the turned stock. And this stock has been given as our starting stock for all our machining technologies. By the way, it's not essential to have this turned stock. You could even still go without a turned stock, but this is much more easier and better for you to visualize when you do the simulation. Okay. So let's start with our new operation of multi-blade machining. Our multi-blade machining currently supports 4 operations. Roughing. It also includes, the roughing also includes rest roughing, by the way, because if you copy the same roughing and add it next, it calculates the stock of the previous operation and only machines those areas where significant amount of material is remaining. Then we have the option to finish the blades and option to finish hub and option to finish the fillets. Now, there are some terminologies that we must understand. For example, the surface at the bottom, this surface is called as a hub surface. These yellow colored surfaces out here, group of yellow colored surfaces, constitute the main blade. And the portion of that also constitutes the fillet of the main blade. The dark green colored surfaces here represent what we call as a splitter or the smaller blade, and the fillets of dark green color also constitute the fillets of the splitter. The longer edge here, which is not visible, so what I'm going to do is I'm going to make a 3D sketch, and I'll drop a line from this point, let's say, to this point. This edge on the side is known as a leading edge. Okay, that's the terminology. Whereas the edge here is known as the trailing edge. The smaller edge is known as the trailing edge. The surface on top out here, these surfaces, okay, there's a group of few cut surfaces. So these surfaces are known as the shroud or the upper area of the multi-blade. It's important to understand what each of them mean because we use a lot of these terminologies inside our multi-blade technology. Right, so let's start with our roughing technology. And we have the strategy here. We have parallel to hub, parallel to shroud, morph between hub and shroud. Although the most nicely looked toolpaths will have morph between hub and shroud, the most practical toolpath will always be parallel to hub. Okay, it might not look beautiful, but it's the most practical toolpath, doesn't waste any time running or cutting air, and it does its work beautifully. So remember to use parallel to hub most of the times, especially when you have a turned hub with you. Okay, so I'm going to define the set of surfaces which define the blades, splitter, and the fillets. Now you can have more than one splitter, you could have more than one blade. Okay, so you need to define a group that defines the blade, a splitter, and the fillets. Okay, I've seen in some cases users just select everything that's available to them. It's not wrong per se, but it's a waste of time to calculate everything. You can just calculate one area and then use the rotation function to copy it to the other areas. Okay, so you need to have one group of these surfaces. So I'm going to define main blades -1 because I already have a option. I already have a group by the name main blades, and I'm going to pick the color from the model and find all the group of faces. So these are the group that I need to select for my roughing. Okay. The next one, since I've said I'm going to go parallel to the hub, I need to select the hub surfaces. Okay, another important thing here is with our multi-blade is that you do not have to select everything of the hub. Just one piece is good enough. One piece is good enough for SolidCAM to generate a curve out of that surface and make a revolved surface internally. In many cases, okay, in many cases, I have got a support request that when you are selecting the hub, Multiblade gives an error saying that it's unable to create the hub surface. Okay, this error comes from those surfaces which were not created using the revolution technique, but were generated using some patching up or NURBS-based technique. The only way to check them is to create an offset of this surface, or rather a copy, and untrim the surface to see if it is really generating a revolved surface or it is doing some crazy surface. So when you don't have a surface of revolution on the multi-blade geometry, you will get an error saying that it's unable to extract the hub surface. Okay, in that case, you will have to manually create a curve and revolve that to generate the surface and define that surface as a hub surface. So you need to define 1 or 2 bits of those surfaces, which is good enough for SolidCAM to generate a surface of revolution, which is going to be defined as a hub. So in our case, I'm just going to pick one, maybe this piece and one of this. Okay, that should be good enough for us. And I will say this is hub -1. Okay. I would like to keep about 0.5 millimeter stock on the blades and splitters and about 0.5 also on the hub. The tool here I'm going to use, by the way, we support all the possible tools that you can think of. We support bull nose cutters, we support end mills, ball nose, taper ball nose, taper mills. We support all these cutters. However, a word of caution, the taper ball nose gives you the best results for roughing. It's also very good for axis movements on the machine. So try and use the taper ball nose as much as possible. If not, if you don't have any other option, then the only option left out is a bull nose or a ball nose cutter. Okay, so I'm going to use a 12 with a tip radius of 3 and an angle of 5 degrees here. This is from Emoog. I've picked up this tool from Emoog. It's exactly represented the way they have asked us to represent. So I'll pick this tool. And in the levels, you can see that most of the things are automated because this is a specific functionality developed to machine impellers and blisks. If you try to use this functionality to do port or, for example, swarf, it will not handle that. It will just return you with an error because this has been written specifically for those applications and it is expecting the geometry to be in that fashion. So the clearance you can see is mostly automatic. It's defined by a spear and it's automatically detects the dimension and the position of the spear based on our current part and the coordinate system. In the toolpath parameters, all I need to define is the cut tolerance, which is set to 0.1 by default, which is good enough. Although it's an overkill to use 10 microns for roughing, but you can leave it at 10 microns unless you have major calculation issues. 10 microns looks good. For the splitter and tool axis smoothing, I would suggest you to leave it at default and work only with the tool axis smoothing if you see a lot of C-axis movements happening on the machine. For example, the tool is coming to the end at this point, and then from this point, the tool is just sticking to the end and it's rotating around with the part in just C-axis. There's no change in A or B, but the C-axis is just rotating. If you see such a movement happening quite often in your roughing or finishing toolpaths, the culprit is out here in the tool axis smoothing. I suggest you push it up to, let's say, about 75 and keep it at 75. You'll see that problem of the C-axis completely rotating every time there's a movement will disappear. Okay, but otherwise 20 looks perfect. Okay, don't have to fiddle with 20. If you don't have any issues with the C-axis rotating, keep it at 20. In the technology, you can define the depth of cut either by number of slices or by the depth of cut itself. In our case, it's going to be 1 millimeter. And the side step could be defined as a number of slices or as a side step. So I'm going to say 2 millimeters is my side step. And then you have the option of rest material. I told you that roughing also supports rest roughing. So you can have rest roughing to be done. For example, somebody has done a 3+2 roughing and given you this stock. Now you can use that stock to generate only the passes where it has material. So it will generate like a rest roughing toolpath, 5-axis roughing. But generally avoid this. Why? Because you will get too many air passes, because it will find material here and then it'll keep jumping between these areas. So that's why you have an option here to avoid incomplete areas or just ignore. Even if it's incomplete, it will generate a completely full area. Now, if I click on avoid incomplete areas, it'll check where the stock is remaining and only cut on those areas where the stock is remaining. Else, if I use the rough layers, it will just ignore where the stock was remaining or not and generate the passes completely on the entire area. Okay. And then you have got an option called as first slice number of intermediate, which means that the very first cut that it will get into the part, it gets a full width of the tool, which is not good when you're cutting materials like stainless steel and Inconel. So in order to avoid that, you can say put 5 passes. Okay, so it will distribute the depth of cut of 1 millimeter into 5. So it will put 0.2, 0.2, 0.2, 0.2, about 5 passes at the start, and then it will start moving sidewards. This will be like you're opening up a slot, and once the slot is opened, you will start machining on the side. Okay, yeah, let's keep it 0 in our case. Now let's go to sorting. So sorting, it's pretty clear. You have one way or zigzag. I would like to start zigzag and start from the leading edge. Again, the leading edge is this side, the large edge. And in the ordering, I can go left to right, right to left, from center away climb, and center away conventional. Let's go left to right. Edges, you've got edge rolling. Now, what is edge rolling? I said there are 2 edges in this case, a leading edge and a trailing edge. So SolidCAM is asking, what do you want me to do on this edge? Do you want me to roll over this edge or just stop much before this edge is encountered? So we can say either automatic or full without trimming. I'll show you in the finishing what this means. Trimmed by the tool radius, trimmed by length, or trimmed by angle. So you can say you can trim it by tool radius, and the tool path will be shortened both at the leading edge and the trailing edge by and value equivalent to the tool radius. Okay, or the same thing goes by the tool length. You can define how much you want that in the leading edge and how much you want that on the trailing edge. This is for trimming, and then you can keep an automatic option which basically will keep the tool path exactly to the size of the blades that were selected, roll slightly on the leading edge, and that's it. It'll leave it there. Okay, let's go to tool axis control. You can see there's nothing much to handle in tool axis control because most of the things are automated in such a way that you really would not need any tweaking of these values unless you encounter issues. For example, you hit a machine limit. It's going beyond a certain value. In that case, you could switch on a machine angle limit and limit the values within those 2 angles. Okay, in our case, I do not think we are going to hit our limit. Let's go to the link. Again, everything is automated, but we are going to change this links in our finishing toolpath to make it look much better and cut much faster. Gouge check only if you feel that there is a gouging on the part of the shank or anything touching the blade. You need to switch on the gouge check. Otherwise, most of the times this software already does gouge checking internally and generates the toolpath. Okay, so let's save this and calculate the toolpath. This would take about 10 to 15 seconds for the calculation to finish. There are about 37 slices. For people who have been working on 5-axis from a long time, machining such an impeller without generic 5-axis is actually a nightmare. I mean, it's a nightmare for every 5-axis solution that is existing under the sun today. If the user starts using this generic 5-axis for this part, then there are a lot of problems. Basically, problems starting with the fillet itself and the problems created by the splitter. Okay, so people who have machined this or used a generic 5-axis know the pain of using generic 5-axis for such complex parts. All right, we have a toolpath here. However, there are some small issues out here. You can see that there are some retracts and stuff like that. Now, what you can basically do is, when you get such problems, the first thing is to look whether your geometry of hub has been proper or not. So let's edit the hub geometry and let's switch off the surface out here. Sometimes this surface could be the culprit. Save it, and maybe let's change the cut tolerance. Let's make it 0.5. Faster calculation. Okay, done the calculation. Of course, it still doesn't sort out, but sometimes you can just leave it as it is. The major issues arise when you start getting retracts out in the front here, and that's basically caused by the hub surface. You don't really need to select the straight surface out here as a hub. You could just select a portion of this and leave that as our hub surface. Okay. Now let's go and try and finish the blade, which is pretty simple. Again, let's go into the multi-blade machining and let's hop for finishing. And in the geometry, I'm going to go morph between hub and shroud. Again, there's a fourth option now for finishing, which is basically swarfing, single pass. Okay, it uses the swarfing engine of SolidCAM. It uses a similar parameters but generates a single pass toolpath around the blade. So let's use the morph between hub and shroud. Swarfing to be used only when you are 100% sure that the cross section is a straight line. In the event the cross section is not a straight line, I would not suggest you to use a swarfing option. Okay, let's define the blades, splitters, and fillets. So in this case, I'm going to pick from the model the surface, and I'll find the group of surfaces. Okay. The hub I already have here. let's say hub 1. And the shroud, let's define the shroud surface. 1, 2, and 3. These are my shroud surfaces. Okay, I'd like to keep about 0.5 for the hub. Let's go to the tool. I'm going to use a different tool this time. I'm going to use a 10R corner radius 3 taper ball nose with a 4-degree angle. Not this one. I would like to use the one with the holder. Okay, most of the things here are more or less similar to roughing, and the only difference here is that you have got a contour. Whether you would like to trim or machine the entire thing, let's use the full and see what is the option that it generates. You also now get an option, because if you use the hub or morph between hub and shroud, you now get the area to be machined. 100% means the entire blade along with the fillet will be taken into account, or you could say start at 5% below the shroud and end at 5% above the hub. Okay, you can define your area, especially if you're not getting great cuts on the top area where the tool is tilting too much. You could reduce the start point and say start at 5% below the shroud. If you're getting good cuts, I would suggest leave it at the default values. And here we are going to say one way, start from the leading edge, or one way, start from the trailing edge. Now, since you have said full, you get another option to spiral around the entire surface. So I'm going to say spiral on the trailing edge, or the best, one way on the trailing edge. So it's going to do a one way starting from the trailing edge. Again, tool axis, there is nothing much. The default works fine unless you would like to control the limits of the machine. Okay, let's save it and let's run the calculation. This is much faster. Okay, calculation is done, and you can see what is happening here is it's trying to run around this surface. Now, we have not selected the surface, so it's natural that it is going to collide or gouge into the surface, which is evident in this tool path here. You can see that it's colliding. Obviously, the full is not going to work in this case, so let's switch off the full and we'll say just trim the trailing edge. That means don't cut this surface, ignore the surface, and stop the toolpath exactly at where this edge ends. Okay, let's run the calculation. Okay, now you can see that it has stopped at the edge exactly, but you have a problem. There are too many retracts. It's jumping from start to end, so you will have a lot of retract. The toolpath doesn't look really nice or appealing visually to the user. So what we will do here is, because the link was controlled automatically, we will override certain links. For example, when it's connecting between the layers, I would not like it to go to the clearance plane, but I would like to blend a spline. Let me run the calculation now. I'm just overriding the automatic functionality of SolidCAM, and you can see that I get a much better and nice looking toolpath, where the toolpath will continuously, almost like spiraling, it is going to run on the machine. So let's run the machine simulation. Okay, that's here. Let's run it slowly. You can see that it just rotates around clears the trailing edge and takes a depth of cut. So once it engages into the part, there is no more further disengaging from the part. Okay, it will disengage only when it has finished the cutting. So it's a pretty important feature to make the toolpath look visually appealing. Okay, so now what we can do is we can simply copy this operation and paste it below. By the way, for finishing, you could also use a set of 3 blades. So it will machine the set of 3 blades together. But then the problem arises, how are you going to rotate it? Because then it becomes tricky to rotate this toolpath. So it's better there to just machine single blade and then rotate this whole thing. So what we are going to do is, let's count the number of blades. We have 1, 2, 3, 4, 5, and 6. So let's edit this toolpath and let's go to our stock and transformation. And in the rotation, I need to define the number of segments. So it's going to be 6. And the rotation axis will be taken automatically by SolidCAM. It'll figure out which is what is going to be the rotation axis around which I need to rotate this toolpath. And do you want to machine all, or do you want to machine some of the segments? For example, I can say machine only 1 or machine 3. Okay, but in this case, I'm going to use, or I'm going to machine all the 6. Let's run the calculation. Okay, and you can see that it machined. Let's switch off the edges, and you can see that it machined all of the 6 segments. Let's repeat this for the small blade. And the geometry in this case, I'm just going to change the geometry, and that's the best part about this. I'll pick from the model, and I'll find the faces. Okay, that's it. Okay, and all I need to do simply is to hit save and calculate. I don't need to change the shroud because the shroud surface remains the same for either hub or for the splitter. It doesn't change, so I can simply just run the calculation. Even machining this with our regular engine is a big task. Okay, so I will go again to stock and transformation and say 6 here and machine all 6. Calculate. Okay, so I have all the 6 segments machined. Right, so we have done with it. We can now attack or move to another part of machining, which is basically the finishing of the bottom hub. Okay, in this case, I will use the same main blades, okay, and I will use the hub as it is, and select a different tool, or probably the same taper ball nose, 10R1 or 10R3, sorry. And in the technology, I will define my maximum distance as the step over. That's the step over, so it's like 1 millimeter. Sorting, we are going to do zigzag. Now this time I'm going to start it from the trailing edge, and I'll go from left to right. Okay, perfect. There's nothing else that needs to be done. The best part about these application-based strategies are they're simple to define, and very powerful results are generated out of it. Okay, so you can see that we quickly generated the option. Now let's look at some functions here. These functions are basically the smoothing. So let's go to toolpath parameters, and then you have the splitter line smoothing here. What happens if I keep it at 0? Okay, you can see what happens if I keep it at 0. You'll see that it tries to come as close to the splitter geometry as possible. It's almost like 0. It comes close to 0 of the splitter geometry. And if I keep it at maximum, it will try to move away from the splitter geometry so as to create a very smooth motion. A smooth motion. You can see that it is just moving away from the splitter geometry. The side effect of this is you're going to have some material remaining out here. So a compromise or a more acceptable solution found out by the developers is about 20%. Okay, 20% gives us a more acceptable kind of a result where you don't have all those issues of material remaining and stuff like that. It does a pretty neat job, and so just generates a nice finish also. Okay, let's come to the last part of the multi-blade finishing, and that is to finish the fillets. Most important and the most toughest part is to finish the fillets. People, again, with generic 5-axis experience will realize how difficult it is to machine the fillets. But in our case, in multi-blade machining, it's very simple. Select the, let's copy this, or let's add straight away, multi-blade, fillet finishing. In the geometry, I simply have to define a portion of the main blades. So one complete blade I need to define because I'm going to machine the fillets of that. And the hub, the tool we're going to use is the same 10 taper ball nose. And in the toolpath parameters, we have got new options the way the cuts are determined. Okay. First of all, we are going to trim it on the trailing edge. We are not going to run the tool completely. And then we can define how we are going to distribute the cuts, either by number of cuts or by big tool diameter. Now, what does big tool diameter basically do is it takes the diameter, whatever we define here. If we define this as 5, it will roll that diameter of spear along the edge of the blade and try and find out the area where the spear is touching both the hub and the blade, and find out what is exactly the area and use the side step and machine only that area. In this case, the number of cuts here are going to be defined by the spear diameter which is being rolled and generating the contact points on both the blade as well as the hub. And that will generate the area, and then the area is distributed by the side step. Okay, it's as simple as that. Or you could just say by number of cuts, I will say I want 5 cuts on the hub side and 5 cuts on the blade side and 5 on the hub. And the side step here is 0.2. Sorting, it's going to be one way. And in the link, however, I'm going to switch off again, not this portion. In the layer, I'm going to have direct or blend spline. Let's save and run the calculation. You can see that in spite of having a not so good data, the machining is really performing really fast. If you compare it with our generic, the amount of time that we spend in defining the data, it's pretty fast. You just select the set of surfaces and you're ready to generate a toolpath. Done the calculation. However, you can see why it took such a long time. It's because I had defined all these as one set of blades. So I have now generated one single toolpath. Should not have been. I should have selected the right set of geometry. So let's change here. And let's select the main blade. No, not this, sorry. Let's check which are the main blades here. Oops. Looks like we have a problem. Okay. What we are going to do is just quickly shut down SolidWorks. By the way, since I'm working on the DV version, it probably could be an issue. So let's start again. And I'll quickly show you a generated toolpath on how the fillet finishing should look like. Okay, let's open a part. Okay, I have this part here. And one of the toolpaths that were already generated, I already have the toolpath, so let me unsuppress that. And this is how my fillet finishing looks like. Okay, so you can see that the toolpath runs around the fillet, both from the hub side as well as from the blade side, and it's linked pretty nicely using a nice spline that's blended between the toolpath start and the toolpath end. Okay, and if I show you the result of the main blade, and this is how this one. So unsuppress this, switch on. This is the finishing of the main blade. You don't need so many cuts. You hardly need about 2 to 3 cuts from hub side and also from the blade side. And also remember that since you're going to run the fillet finishing, you can stop the hub finishing from the blade by 0.2, 0.3 away, so that when you're finishing the hub, your tool doesn't touch the splitter blades or the main blades. So you can just stop them much before, and the remaining portion of the finishing will be done by the fillet finishing itself, so we don't have to worry about matching and other things. Right, so today we have come to the end of part 5, where we saw a couple of options in generic 5-axis, and we also saw our multi-blade machining. In the next couple of webinars, we'll be touching upon the port machining module of SolidCAM and also the swarfing of SolidCAM, and then we will end it with multi-axis roughing and edge breaking in 5-axis, which is our contour 5-axis technology. Right, I'm done with it. If there are questions, you can either ask them now, or you could even send those questions to me via Skype or email, and I'll do my best to answer it back as soon as possible. Thank you very much.
Okay, Amos, thank you very much for the webinar. And as you said, next week we'll have the next part of the 5-axis simultaneous machining series of webinars. All right, so take care, everyone, and have a great weekend.